Hello, my name is Nikolai Kuber, and in this video I will show you how to integrate VREP with Python. For this purpose I will be using a Pioneer P3DX robot, and I will show you how to send actuator commands to the robot's wheels and how to capture proximity sensor information as well as image data and transfer it into Python. I'm using Python because a lot more people are familiar with Python than they are with Lua scripting. In addition, using a more familiar programming language like Python will allow you to use libraries that are commonly used in academia and industry. In this video, I will be using Python XY distribution, which comes with Spyder, which is a programming interface that has MATLAB-like features. For example, it has a variable explorer, which allows you to see all of the variables that are currently loaded. So let's begin this tutorial. We begin this tutorial with a blank scene. Click File, New Scene. And then under Model, in the Model browser, which you can open and close with this robot button, under Models, Robots, Mobile, select and drag this Pioneer P3DX robot. I'm just using this particular robot because I've had a chance to use it in the past, and also it's a little bit more exciting than just having a cube drive around your scene. So right-click anywhere in this scene, select Add, Vision Sensor, and then Perspective Type. Drag it around until you have it somewhere where it's looking at the robot itself. And you also want to rotate it so that it points towards the robot. And then elevate it slightly. The other thing that you want to do is we want to see the output of the camera. So right click anywhere in the scene, select Add Floating View, and then with the vision sensor selected, right click on the floating view, select View, and then associate view with the selected vision sensor. And then you can run the scene and you'll find that it just shows black. The reason is because currently the field of view VREP has a near and far clipping distance, so we're going to have to change the field of view to be wider and longer. Double click on the vision sensor icon and then select under near far clipping distance, put this to something like 2 meters and maybe increase the resolution to 128, make it 64 by 64. And then you'll see that it's actually upside down. You can easily change that by selecting the object item rotate, and then under gamma type in 180 degrees, and there you have it. So the other thing that I would like you to do is under vision sensor, since we're going to be working with handles, make sure that you name your objects appropriately. So here, this one, I'm just going to call it Cam1. And there you have it. So now we have set up the scene. Actually, let me just add another thing here. Let me add a cuboid. And this one will just remain in the scene as a moving object because the Pioneer is probably going to drive off. Now add an actuator, joint prismatic, and then make sure to attach the cuboid to the prismatic joint. So what happens when you run this? You'll see that even though the cuboid is directly in front of the camera, it's not actually showing up as a target. So what you want to do is you want to make sure that the object is also renderable. Double click on the cuboid, select Common, and then Renderable. Now when you run it, you see that the cuboid actually shows up. The other thing that I want to do is I want to make sure that the cuboid actually moves up and down. So I'm going to double click it, select common, and then I'm going to select shape, show dynamic properties. I'm going to set it to static. And under prismatic joint, I'm going to set it into motion mode and adjust the motion mode parameters and give it a velocity of something small. So now the cuboid moves up and down and the robot drives off. The other thing that I want to make sure is that I set the limits, and maybe I'll set this one to 0.03. This will mean that the cube will only drive up to 0.03. It currently disappeared because I maybe set this to 0. And there you have it. So now we have set up our scene, and we can now move on and start doing things related to Python. Now that you have set up the scene, you can go ahead and download Python XY. You can get it from code.google.com. I will set a link in the description as well as a link right here. Download the latest release and go ahead and install it. This will actually work with any kind of Python release, I'm pretty sure, and also with most other graphical user interfaces. Again, I'm only using this one because it has a very MATLAB-like interface through Spyder. After you have downloaded and executed Python XY, you can run it. Then you will get this following window. Here you can run Spyder with this button, or you can also see all of the Python modules that are currently installed. You have NumPy, SciPy, you have some image processing. It does not currently have OpenCV, but you can add it later. Specifically for this tutorial, we'll need NumPy and Python imaging library. NumPy allows you to manipulate arrays in a very much similar to MATLAB-like manner, amongst other things. So you can run Spyder with this button. It takes a while, so I've already started it up, and you'll get the following window. Again, I'll just start a new file. What you have here is a very MATLAB-like interface. Here you have your script that you can write and save. Over here you have Object Inspector, the File Explorer, a Profiler, breakpoints, and this Variable Explorer. This Variable Explorer is actually the main reason why I'm using Spyder. It's because it allows you to see the currently stored variable. For example, if you have k equal to 7, it shows up right here as a type, the size, and the value. This is a very, very helpful feature that will allow you to debug your code as you're writing it. Here you have the console window, and here you can essentially just write commands and test them while you're writing your code, so that you actually know exactly what's happening. Unlike in C, where you where you don't always have that luxury. And then here you have the console and the history log of all your previous commands. So that's something that's also useful because that way you don't ever forget a command. Now that Spyder is set up, you will have to copy some of the files needed to interface VREP with Python into your working directory. Navigate to your VREP installation folder, which should be located somewhere on C program files /VREP, and then select Programming, Remote API Bindings. This particular folder has all of the files needed to interface VREP with Java, MATLAB, Octave, or Python. We'll be using Python. you will have to copy all of these files into a working directory. For me, the working directory is just a folder I created on the desktop, so I'll just copy those in there. In addition, you will also need one library file, which is located in the lib directory. Since I'm using the 32-bit version of VREP, I'm going to use the 32-bit file. Alright, so now we have to point Spyder towards this directory, and the way I'm going to do it is I'll just save my script in this folder. And I will call it just VREP main Python. So, and here you can see that this the current directory is pointed to the correct folder, and you can also test it by typing import vrep. Since it did not give you any error messages, this just means that it was able to find the vrep.py that is also located in the folder. The only other thing that you will need to add a command into vrep telling vrep to start something that's called an API server. The command for it is actually in simpletest.py. If you click on File Explorer and open the file, just right-click and select Edit. Here you have to add the command sim external remote API start, and you have to place it somewhere in vrep so that it knows to start the remote API. And this command only has to be run once. So it's not recommended to add it anywhere in the main script, so I'll just add it in the cuboid. It can literally just be anywhere. And I'm going to right click on the cuboid and select add, and then associate a child script, and now select a threaded child script. Now double click on this scroll icon, and here you have, unlike in my previous videos, now you have the threaded function comes first, and down here you have some initialization code. So just paste the sim external remote API start code right here. The thing that you should note is that this particular value here is the port on which the remote API server will run, so you can just leave it 19,999. Also, you can only connect to vrep when the simulation is running, so you will have to keep it running while you're working on your code, or when you're running the code. And to prevent the Pioneer from driving off while I'm busy writing the code, I'm going to go ahead and I'm going to look at the code that the Pioneer robot has by default. By default, it has just a simple example navigation program, but what I'm going to do is I'm going to disable that program because I want to be able to send it commands to the actuators. The way you disable a script is to click here on scripts to see all the scripts that you currently have, and here you have the non-threaded child script of the Pioneer 3DX, and just click on disabled. Now when you run it, it's nice and stationary, and this allows you to work with your code without anything driving off. Let's run simpletest.py, which goes through the basic steps of how to connect vrep to Python. Make sure that your simulation is running, and then go on to Spyder, and then open simpletest.py and run this program. You can run it by pressing F5. I'm getting this warning message because I currently don't have a Python console selected. So here under console, just select Python 1. And again, go back onto the simpletest.py and press F5. Here, now you get the output. Anytime there is a print command, you will get some kind of an output here. What's happening here, the first command, vrep.simxfinish, closes all open connections. And then simxstart establishes a connection between Python and vrep. And then you have print connect connected to remote API server. That's right here. And then what this sample file does, it counts the number of objects in the scene and prints out the number. For the rest of the tutorial, I'm going to take these elements from simpletest.py and add them into the vrep main Python, which is a custom code. And I will first control the Pioneer 3DX robot by just sending it actuator commands, and then I will also show you how to capture images from vrep into Python. We begin the script writing with the IPython console. In this console you can prototype any command that to verify that it works before you actually put it into your main script. So the first command will be import vrep. This one allows us to just loads all of the library files necessary. The second command will be vrep.simxfinish. And this is just kind of a cleanup command. And it's good to have. The next one will be a command, this vrep.simxstart command. This one returns a client ID, which we will need for every single command that we will run when we're using Python and vrep. It also takes in quite a few of parameters, and if you want to know what each of these commands does, you can look it up in the remote API documentation. This one is on the CoppeliaRobotics.com website, and I will add a link to it as well. If you scroll down to simxstart, you get a description and all of the parameters that it takes. So the first parameter is the connection address, which is 127.0.1, which is just a local IP address. Then you have the connection port, which is 19,999, which you previously set in the vrep code. The next one is wait until connected. It's just a boolean to make sure that the program waits until a connection is established. The next parameters do not reconnect once disconnected. And then we have this timeout in milliseconds, which means that the program will try to connect for 5 seconds. And this last parameter is the thread cycle. And this one indicates how often data packets are sent back and forth. This is essentially sending your update rate. Right now, with 5 milliseconds, it's set to 200 Hz. And I didn't actually test this out, so you'll have to see whether there's a limit on how much data can be sent between Python and vrep. So we run this and we get client ID 0. This is actually what we're expecting, because in the simpletest.py it says if client ID is not equal to -1, meaning it will return -1 when no connection could be established. And then else print connection successful. One thing that we want to do, we want to quit the program when no connection could be established. Sorry, it's connection not successful. And in order to quit a Python program, we'll need the sys library, So when connection could not be established, we just go sys.exit. And here we can set an error message, and we can say error could not connect. And you can also test whether it works by copy and pasting it. And you get connected to remote API server. So everything's fine. We can actually test if our connection code is successful by simply stopping the simulation in vrep. And then when we run this code, you will get system exit could not connect, meaning that the client ID is -1. And then we can run this again with the code running, and you simply get connected to remote API server. vrep in Python works a lot like vrep and Lua scripting. First, you have to get a handle to a specific object that you want to modify, and then you run the modification function and you send it the handle of the object. So the first thing we have to do, we have to get a handle for the robot. Now vrep has a couple of functions for that, and we can look at all those functions by going vrep dot. The suggestion dialog disappeared because I typed too much, but if you press Ctrl and space, you can get it back. So what we want something like simx get object handle. And then when you open the bracket, you will see that it takes client ID, object name, and operation mode. It's always recommended to look up the documentation for every function that you are about to run. So in the documentation, it says that the first one is the client ID, then you have the object name, and then something called the operation mode. So first, let's take the client ID, which is just right here. Again, you could just say 0 instead of client ID, because that's the actual value, but let's stick with the return values that are given. The next is the name of the actuator that we want to modify. The Pioneer 3DX script actually has the names Pioneer P3DX left motor and Pioneer P3DX right motor. So we'll just take those. And you can also see the actuators here as child objects of the robot itself. And then we have this parameter at the end called the operation mode. It's when you look at the documentation, it says that the recommended operation mode for this function is simx op mode one-shot wait. And if you look at the documentation, it says the command is sent and the function will wait for the actual reply and return it. So as there's different operation modes. For example, there is streaming, where the command is sent and the previous reply to the same command is returned, and then the command will be continuously executed on the server side. But in this case, we only need, we'll just use the recommended option. Okay. In addition, if you look at the Python synopsis, we actually want to take it returns two numbers. The first one is the error code and the second is the handle. So let's write it in this following way: error code, comma, left motor handle equal to. Okay, so Now this command is finished. Let's try running it and see what happens. When we run it, you get this error message. SimX op mode one-shot wait is not defined. And the issue here is that SimX op mode one-shot wait is a variable of the vrep library, so we have to say vrep dot. And now the command successfully executed, and you have a few things here. Here you have the error code, which is 0, and here you have the left motor handle, which is 18. What would happen if we asked for a handle of an object that wasn't there? Then you get error code 8 and the handle of 0. So now that this command works, we can take it and put it into our script. And we can do the same thing for the right motor as well. And again, we should verify that it works. We have error code 0 and right motor handle 15. The only thing that is left is to modify the joint velocities. Again, I'm not entirely sure how this Pioneer robot was made, so we'll look at the pre-made script. And in the pre-made script, to get the robot to drive, they use the command simset joint target velocity. So we'll have to look for a Python equivalent of that. So let's go vrep dot and then simx, and we want to set and the object case is very important here. And then let's look for joint target velocity. And again, we have client ID, joint handle, target velocity, and operation mode. So let's add client ID and then the joint handle, and we'll set left motor handle here. And then we have the target velocity, which we'll set to 0.2. And then again, we have this operation mode. Let's verify what the operation mode should be. And here it says recommended operation mode for this function are simx op mode one shot or simx op mode streaming. I'll just select streaming. And again, remember to put vrep dot in front of it. Okay, so let's see what happens when we run this code or this line. And then the robot right away starts to turn because its left wheel was commanded to drive. And the thing that you should note is that it'll actually return an error code. So in this particular case, it returned 1. So I guess just for the sake of completeness, we can say error code equal to. And in your main script, you could go through and make sure that the error code was 0 or 1 or whatever it is, and make sure to start printing out if something is wrong, so that you know if, for example, the object handle was not found, or if for whatever reason it could not set a target velocity. Okay, and we can do the same thing for the right wheel as well. And since both of them are currently set to 0.2, I'm not entirely sure what the speed is, meter per second or what have you, the robot is currently driving forward. So there you have it. Now you can set robot joint velocities from within Python. The Pioneer P3DX has 16 onboard ultrasonic sensors, which are shown in yellow all around the outside perimeter. These sensors are shown right here and are labeled ultrasonic sensor 1 through 16. We can access their information and send it to Python by first getting a handle to that object. And we're going to do the same thing we did for the actuators by using the vrep.simxgetObjectHandle command. I'm just going to copy and paste it and rename it sensor1. And here, rather than left motor, I will call it ultrasonic sensor1. After you run this command, check the error code. It's 0, so it means that everything has returned fine. And sensor1 is number 35. vrep numbers all of its objects in the scene hierarchy from 1 to however many objects there are. And in this particular case, the sensor1 is object number 35. Next, we need to run a function that will allow us to read that sensor. For that, we're going to look into the remote API function list for something called simxReadProximitySensor. And here under Python synopsis, I'm going to just copy and paste this entire block of code. Well, it's actually just a line of code. This Python synopsis explains to you what the return variables are, and also their type, and what kind of inputs it takes. So after I've copied and pasted, I'm going to just remove the types, because Python does not do types. I mean, it just automatically assigns it to a specific variable. And then again, we're going to have to put vrep dot in front of the command. So here we have error code, detection state, detected point, detected object handle, detected surface normal vector. Those are all the names of the variables that will be returned. And then here we have the name of the function. And then here are the input arguments, which is client ID, and then number sensor handle. Here I could just give 35, or the variable name, which is sensor1. And next we have the operation mode. If you read in the API function list, it tells you that the operation mode, the recommended mode is first running simxOpMode streaming on the first call, and then run simxOpMode buffer. So for example, the first call could be outside the for loop, and then during the simulation, you will run this with the operation mode as buffer. Since we're running this for the first time, let's use this particular command. Oh, and because I have forgotten to put vrep dot in front, so now we run this again, and we see that it has returned a whole bunch of variables. This is on the first call. So now that everything is initialized, we can go ahead and change this last to simxOpMode buffer and see what happens. So now it ran, and we have a detected point, a detected surface normal vector, a detection state, which is false, which means that it didn't actually detect anything, but the error code is 0, which means that the command executed OK. So Let's try and find out exactly what happened. If you look into the simulation environment, first let's locate the ultrasonic sensor 1. When you click on the sensor, you will see this localized coordinate frame of the sensor. And you will find that it's this one right here at the corner, and there is now no object in front of it, and that's why the return state is false. Let's modify the scene by adding an object in front of it. We're going to have to stop the simulation for that, and then select add primitive shape, and I'll just put a simple box in front of it, but I'll make it large enough that it will be detected. Okay. The other thing that we have to do, we just added a new object, but we have to check the object special properties, and we have to select detectable. Otherwise, the object will not be detected. Now we can restart the simulation, but we will have to reconnect to the remote API server. So first, let's run the vref.simxfinish command. And then we can run client ID equal to vref.simxstart. Okay. So let's get the object handle. Previously, the sensor 1 was object number 35, but since we added an object, I'm not sure whether that handle has changed. So let's rerun the command where we get the object handle. And when you partially type a command in the IPython console, if you press up, it will suggest the most recent comment that you've written that partially matches what you've typed. So let's rerun the command. And error code is 0, and sensor 1 is still object number 35, so we didn't need to run that command. Now let's see and run the vref.simx read proximity sensor with the operation mode as streaming, which is how you're supposed to run it the very first time. And again, everything returned good, it's all initialized. And now run it with buffer as operation mode. And now you can actually see that the detected object handle is number 60, which I'm assuming points to cuboid 0. There is a detected point, a detected surface normal vector, and the detection state is true. So now you know how to get information from the proximity sensor into Python. To clarify the readings that you received from the ultrasonic sensor, take a look at the detected point variable. It's a three-dimensional list which has a value which is essentially near 0 here, 9 times 10 to the minus 5, another one of 1 times 10 to the minus 5, and then here a value of 0.3865. So this corresponds to the x, y, and z value. Take a look at the ultrasonic sensor on the Pioneer 3DX robot. And you can see that the red arrow corresponds to the x, the green arrow corresponds to the y, and the blue arrow corresponds to the z. So what we've received now is just essentially a distance vector, which is, if you took the norm of it, it would essentially be 0.3865 meters. And you can do that for all other sensors as well. The only thing remaining is to get image data from vref into Python. First, we have to get an object handle. And in our simulation, our camera handle is cam1. and we will call this variable camHandle. And here we can see camHandle has value 55 and error code returned was 0. So now we need a function that allows us to receive those images. We can see the image, all those functions with vrep.simx_get, and then we kind of have to scroll through the get functions. There is get joint force, joint position, and this is a quick and easy way to see what you have available. And here towards the bottom is simx get vision sensor image. When you open the brackets, it takes in the client ID, sensor handle, some options, and operation mode. We will need more information about the options and operation mode, so we will consult the remote API functions, and I've already found the location, which is simx get vision sensor image. I will just copy and paste the Python synopsis and then remove all of the type definitions, and you can see that it returns an error code, an array, which is the resolution, and then the actual image array. And then here we have to preface the function name with vrep dot. As inputs, it takes in the client ID, the sensor handle, and then these two parameters, options and operation mode. For options, you have the option to either get a grayscale image or an RGB. Since we want an RGB, we will set it to 0. And under number operation mode, it's recommended that we use simx op mode streaming split plus 4000 on the first call, and any subsequent call will be simx op mode buffer. Now, what is this simx op mode streaming split? And what is this 4000? When you scroll down here, it'll tell you that what it will essentially do is that it will divide up the data that's being transferred into small chunks, and because small values won't slow down the communication. Rather than using the simx op mode streaming split command, I will just go ahead and use simx op mode streaming, because since I'm only doing this, you will kind of have to experiment to see how fast you can get it. This will be most noticeable if you're using a for loop or a while loop. And under sensor handle, I had to call it camHandle. Okay, so error code is 0, so everything is fine. And now let's run the command again, except now we'll set the the operation mode to buffer. And now we have the image, which we also had previously, and we have a resolution which is 64 by 64 pixels. The error code is 0, so it means everything was returned normally. And that's pretty much it. So now we have the image, which is currently just a list. The size of the list is 12,288. Now we have 64 by 64 pixels, and we have 3 channels, which is RGB, and that comes out to every single entry within that list is 1 number. So the next step will be to just display this image to verify whether we have actually received what we think we did. Now that you have this image data, there is many different ways of handling it. You can use OpenCV, for example. But to be honest, this is image processing and it's kind of outside of the scope of this video. So I will simply display this image in the IPython console to verify that we're actually getting the information that we are expecting to. To properly display this image, we will need two libraries in this particular case. The first one is NumPy, and we're going to run the command import NumPy as np. Now NumPy is a library that has a lot of functions for scientific computing. Now, if you're not familiar with the syntax of Python, import NumPy as np essentially imports the NumPy library and renames it to np so that we don't have to write it out every time. The second library that we'll be using is matplotlib. Now matplotlib is a library that has functions that can display images as well as plots, and it functions very similar to the MATLAB library. And the command that we will be using is matplotlib.pyplot as mlp. And this will just save us a whole bunch of writing. And I can go ahead and take those two and add them to our script. At this point, the script doesn't really follow any kind of shape, but I'll just keep copying things over for the sake of completeness. Okay. Currently, the image is of type list. We want to create a NumPy array which has the image information. So we run the following command. im is equal to np.array. This np.array creates a new NumPy array, and it takes as inputs the list data, which is the image, and an optional parameter, which is dtype equal to np.uint8. What's happening here is that the image data comes in and it's negative and positive. It's coming in as a signed integer of 8-bit, which means that it's on the range of -128 to 127. So here we want to convert it to 0 to 255. And now we have this NumPy array, which we also want to double check what its shape is. Now its shape is currently 12,288 by 1. We want to reshape it into an image form, so we run the following command. im.resize, and then it takes in any kind of parameters into which to reshape that NumPy array. And what we use here, we use the resolution and (3), which is the 3 channels, which are RGB. So we verify again im.shape, and now we have something that's appropriate for an image, which is 64 by 64 by 3. The last thing that remains is to display the image using the matplotlib library. And we can do that using mlp.imshow im. And this imshow command also works in MATLAB as well. So now you can see that this is exactly the same image at that time that the simx_get_vision_sensor_image command was called. One thing you will note though, that this image is currently upside down, and that's because we have to modify this IMShow command by placing the origin somewhere else in the lower bottom. And that's essentially because on all screens, as you go down, the Y value increases, so we just had to flip it upside down. So there you have it. You can now capture an image from VREP and then transfer it into Python. For the sake of completeness, I will take all of those previous functions and add them into a script where a robot moves around an obstacle field at random and just avoids the obstacles. I created the scene by first adding a whole bunch of primitive shapes in cuboid form. When you do that, make sure that the object common properties, collidable and renderable, and detectable, are enabled. This will allow the robot to collide with them, but also to detect them. I've created a script in Python that I'll upload, and I'll put the link in the description. However, I feel that I should probably go over it and explain to you nearly line by line of how it all goes together. At the beginning of the script, I have here all the libraries that I previously told you about. The next line essentially just defines a constant, which is pi, because I'm going to be using it a whole bunch of times, so I didn't want to write math.pi over and over again. These next few lines have all the code needed to establish communication with a remote API server. And if the connection is not successful, it will simply exit the script. These next two lines, you take the motor handles and you store them into the left motor handle and right motor handle variable. The next line contains sensor H, which is an empty list which will be used to store all of the handles for the proximity sensors. The proximity sensors are numbered 1 through 16. And because there are so many of them, I don't want to have to write out simx get object handle like I did up here. I'm just going to automate it in a for loop. The sensor values I'm going to be using for calculations, so I store them in an empty NumPy array. This line is only here for pre-allocation. The sensor location I take from the P3DX manual, and is essentially the orientation of every single sensor relative to the robot center. In this next line, for x in range 1 to 16, I begin a for loop. This range 1 to 16 returns the values, well, it's 1 to 16 plus 1, but it returns the values from 1 to 16. And that's just how Python does its for loops. Rather than writing out ultrasonic sensor 1, 2, 3, I use this strx command, and that one takes a value and puts it into a string. So essentially it saves me a whole bunch of writing. And then once I get this sensor handle, I take it and I append it to the list. And then in this next line, I begin the reading of the proximity sensors. I also take the sensor value because if you remember, the read proximity sensor returns a three-dimensional detected point. So what I do in this next line, I use the linear algebra sub library from NumPy, and I take the norm of this detected object. So essentially I take a three-dimensional number and turn it into a one-dimensional number. And I append it to the sensor values. And then I take the Python time. This script is going to be using the time from Python while VREP runs on its own time. If you have something that's more advanced, like model predictive control that requires a lot of computation, you might want to look into vrep.simx pause pause communication and simx pause simulation. These two functions will essentially allow you to line up multiple packets to be sent to the simulation. But this is not what I'll be doing in this script. So this concludes the pre-allocation, which will be done at the beginning of every script. The next step is a while loop, and this one will be looped throughout execution. And here what I'm essentially saying is while time is less than 60 seconds, which is how long the script will run for. The first thing I do is I read the sensor values of the proximity sensor and put them into the sensor val. The next few lines are controller specific. First, I take only the values from the front-facing sensors 0 to 8 and I square them. I square them for, it doesn't really matter, you can use linear or you can use square values, but I essentially put more emphasis on values that are small. The next thing I do, I find the minimum sensor value, essentially the smallest measurement, which means that I want to find a sensor where the obstacle is closest to the robot. And I use the numpy.where command. Now the return value of numpy.where is a numpy array, so I want to turn it into a simple number by using this following line. In the next if statement, I check if the minimum value is less than some predetermined value. I use 0.2. And then I take this steer value and I assign it 1 over the sensor location at the minimum index. So I find that sensor which has the obstacle closest to it. Now I have to explain why I'm using 1 over the sensor location. If you're looking at sensor location from 0 to 8, which are all the front-facing sensors, you will find that the sensors on the side have a large value, and the sensors on the center or the front-facing sensor have a small value. When you're trying to avoid an obstacle, you want to give most weight to the front-facing sensors, which means that if an object is right in front of you, you want to steer away and you probably need a lot more control effort than if the object was simply off to the side a little bit. So when I go 1 over those numbers, you will see that the front-facing sensors have a much higher weight on them. And then I take this number, I multiply it by -1 to compensate for whether it's left or right. And then here, the v equal to 1 is just the linear forward velocity. This kp is a proportional constant which will scale the steering value. So here I say left velocity is equal to velocity plus kp times steer, and right velocity is equal to v minus kp times steer. In these next two lines, I essentially print out the values, and this is just for debugging purposes. And then in these last two lines, I send the target velocity to the robot, and then I pause the script for 0.2 seconds. This number I've chosen arbitrarily. When you're doing real robot control, you don't want to change this to a very small number, because sometimes you can be sending conflicting commands consecutively if there's either a noisy measurement or kind of a blip in your measurements. So I just set 0.2, which means it executes 5 times a second. And then once this script is done, I also just want to stop the robot, and so I send it a 0 velocity to the left and right motors. So what does that look when it's running? First I run the script, and then I run the code with F5. And now you have the robot advance forward towards an obstacle, and it avoids it. So there you have it. This is kind of how you connect VREP to Python, and I've given you kind of a sample script to start from, and then you can take it and do a lot more advanced control rather than what I've shown you here. This is just a very simple, try not to run into anything. I hope you enjoyed this video, and I plan on releasing some more videos in the coming months. If you have any kind of ideas or if you have any kind of questions, please make sure to let me know in the comments below. Thank you for watching.